All right, I'm very happy to introduce our second cleanup hitter. That's Dr. Bruce Logan. Now, Dr. Logan also won the Clarke Prize, and he won it in 2009. So let's congratulate Bruce on his 2009 award. So he's the Cappy Professor of Environmental Engineering at Penn State University, and he's world leader in all aspects of research on microbial fuel cells and related bioreactors and the bacteria and the engineering that goes along with it. And also, in 2013, he was elected to the National Academy of Engineering. And with that, we'll bring Bruce up.
Thanks very much, Bruce. Well, our water infrastructure takes a lot of energy, so I think it's really time to think more seriously about making our own energy. And if you look at the history of energy, it pretty much began with a campfire, and it hasn't changed a whole lot since then. We've learned to burn other things. We went from burning wood to coal to oil to shale gas, and we still look to other fuels to burn. For a while, we thought maybe we would make energy with nuclear fuels, but we haven't really solved the waste problem with that. So in thinking about the future, where might we look for new solutions? And I would propose that maybe electrochemistry might be the next frontier for energy solutions. We're seeing that certainly with the emergence of increasing roles of solar energy. Wind doesn't really qualify perhaps in that regard, but what about electrochemistry in water? I'm not going to talk about tidal power or hydropower, but just about making energy from water itself. So if you have salt water flowing into, if you have salt water and you have fresh water flowing into that salt water, like you would have with the river or from a wastewater treatment plant, you are essentially throwing away energy because that mixing energy is equivalent to water flowing over a dam 270 meters high. And globally, that could provide, it's estimated, about a terawatt of power. Now, Manny mentioned ammonia and CO2, and this is an idea that came out of his lab. The idea is that you can distill off ammonia and CO2 at relatively low temperatures using waste heat, and thereby artificially create a high concentrate or a salty solution and a low salt solution. And if we can get 270 meters out of sodium chloride, well, we could probably get close to 400 meters out of ammonium bicarbonate. So I'm going to talk to you about how to make use of this. Actually, the Clarke Prize was mostly based upon my work on microbial fuel cells and extracting energy from wastewater. I'd like to tell you how we can build upon that, not only treating the wastewater, but making more power. And I've previously talked about the energy in wastewater and cellulosic energy, but today I mostly want to talk about salinity gradient energy and then using waste heat energy to create this power. So there are, by my count, and that means I'm not including them all, 5 different salinity gradient technologies: pressure retarded osmosis, reverse electrodialysis, something we call CAPMIX, hydrogel expansion or HEX, and thermal regenerative batteries. The first 2 may be most familiar. I'm guessing the last 3 are very unfamiliar to you. So I want to talk about these first couple of technologies in the context of building them into microbial fuel cell technologies to enhance energy extraction, and then I'll go on and actually talk about a couple of these technologies as standalone technologies and technologies that frankly don't need microorganisms. Now, the first part of building these technologies into microbial fuel cells, you would probably say, well, that's the craziest thing I ever heard, because from a business point of view, if you have one technology which isn't yet commercialized and you have another technology that isn't commercialized, why would you want to combine those 2 technologies? But it's not always crazy, because imagine if you want to split a block of wood and somebody gives you a stick. Well, that's one technology, that's not going to work. If they give you a sharp metal object and you try and split that wood, that's not going to work. But if you combine them together, you get a technology which overcomes the limitations of both of those technologies. So some of these combined technologies may work better than others, and we'll explore a few of those, but I just have to make sure you understand what a microbial fuel cell is And so that's where we use naturally occurring bacteria that are in wastewater that can break down the organic matter and produce an electrical current. That current then is avoiding the need to aerate the wastewater, and so we essentially replace an activated sludge reactor with something which generates electricity. We can also modify these systems. This is a two-chamber system where we would need to aerate the water, but we don't want to do that. So instead, what we do is we take away the oxygen, whereupon absolutely nothing happens. But if we boost the voltage from that just slightly, then we can actually evolve hydrogen from the cathode. So this would be a way of making hydrogen in the system. And we can make other fuels in that system as well, like methane. But what I want to first talk about is how might we use pressure retarded osmosis to improve the microbial fuel cell. Pressure retarded osmosis is where you have membranes which allow the water to pass but not the salts, and so the fresh water going through the membrane pressurizes the seawater, and therefore you can extract that energy using a turbine. So if you were to combine that with a microbial fuel cell, what you would have is wastewater on one side and, say, seawater on the other side. You have two electrode reactions, and then as that runs, the water moves into the seawater and pressurizes it, and hopefully helps with proton transfer into that as well. So that's a good idea, but actually it's not that practical because you've got wastewater on this membrane, you're pulling wastewater through that membrane. This is one that's probably not going to work so well. The second one is reverse electrodialysis. Now, to introduce that, let's think about what electrodialysis is. Electrodialysis is a series of anion and cation exchange membranes where you fill the whole system with, say, salt water, seawater. And then you impose a big voltage across that, and all the anions go towards one electrode and all the cations go to the other electrode. But the anions can't go through the cation exchange membrane, so they get stuck, and you get these chambers which are now concentrated with salt and chambers which are depleted with salt. And that desalinates the water. So if you start out with the reverse of that, where you have seawater and river water, for example, in those cells, then you have an electrochemical potential difference between those cells, about 0.1 to 0.2 volts. And if you put enough of them together, you can get electrical current flow, because these act like a series of batteries where each pair of membranes combined add up to the other individual batteries in the system. So imagine the system with a series of membranes and two electrodes on each, an electrode on each side, and you could split water on one electrode, evolving oxygen, and on the other electrode, evolve hydrogen. But you need a lot of membranes to do this. You need at least 10 or 20 pairs just to start to split water, and then you need maybe hundreds to start to harness this energy. So we thought, well, maybe we could just put a few of these membranes into a microbial fuel cell between the electrodes, because we already have a favorable reaction. And indeed, if you move that into the system, you can essentially build in a saltwater battery into the system. And so when we put this into microbial fuel cells, we greatly increase the voltage now from about half a volt to about 1.5 volts. We increased the power up to about 4.5 watts per square meter of membrane electrode, and we had a high energy efficiency of about 42%. So think about that idea now with something like ammonium bicarbonate, where you could do this inland or virtually anywhere that you have this source of waste heat, and you could create this closed loop cycle of salt water and fresh water and add that into your wastewater reactor and provide extra power. Now, you don't just get extra power out of here, you actually make the system work better. So if you look at this solid line here, use the marker for that, that's about how much energy the microbial fuel cell should produce. But once you put that stack in there, it produces that much energy. So you're not only just getting energy out of both systems, you're actually making the system work better. And the reason you're making the system work better is because you're changing the potentials of the electrodes. Here, the electrode potentials, the cathode falls off very quickly, and the anode potential rises as you start to generate more current. But with those red stack in there, they flatten out. And so the idea is you can go to ever-increasing currents and get more and more power, because power equals current times voltage. But you don't really need that many membranes in this system to make it work well. And in fact, on the left, I'm showing power generated from domestic wastewater with no membranes. That's the black diamonds on the bottom. With just one membrane in the system and ammonium carbonate in the second chamber, you come close to almost getting about half the power that you got with many membranes in the system. So with just a few membranes, you can greatly increase the efficiency and power generation, and more importantly, increase the current density, because that means you'll treat the wastewater faster. You can also use the same stack. I said you could make hydrogen if you had a power source. Well, now you do have the power source. That power source is that stack of membranes, or a few membranes right in between the electrodes. So you can do this essentially with the salt water. Now I want to tell you about the hard ones. Those are the easy ones. And these are the technologies you probably haven't heard of. They're called capacitive or battery mixing electrodes, and they work on the same idea of a salt solution. But there are three different types of reactions. And let's consider the first one, which we call capacitive double layer expansion. Everybody had thermodynamics. That's an engineer, right? I'm sure you remember all your thermodynamics. This is sort of like a Carnot cycle. Let me tell you how it works. You take an electrode and you put some salt water in here, and then you apply a voltage which creates a current. And what you do is you draw ions onto that surface. So you're inputting energy into the system and you're moving a current. And then what you do is you disconnect that circuit and you put fresh water in. And now what happens to those ions, they're stuck on that surface, but you put fresh water in and they want to escape that surface. Now they do escape that surface, but in doing so they do work. And when they do work, that has to translate to something, and what it translates to is a rise in the voltage. Then you connect up the circuit, and now those ions will create a current. And so you can actually extract that voltage that you built up, but now you're extracting it at a higher voltage than you input energy into the system. Then you disconnect the circuit, you change it back to salt water, and you repeat the cycle. So let me go through that again. You charge it by putting current in, you pull the ions on, you disconnect the circuit, the double layer expands, that raises the voltage, you reconnect it, you get current out of the system, and then you open the circuit, and you change the voltage back down, and you repeat it. And the energy you capture is basically the size of that voltage window. This should remind you of your Carnot cycle from thermodynamics. The bigger that window, the more energy you can extract. So the equations, thermodynamically, the equations are completely different and exactly the same. That is, here you have temperature and pressure, and here you're looking at potential and capacitance. The second technology is a little bit different, but not much. In this one, you basically apply an ion exchange coating. This doesn't have to be a true membrane. It's just a coating onto activated carbon. And now what happens is those ions spontaneously move on there, and you can do the same 4 cycles without putting any energy in, or you can actually force charge it and increase the window. So these are 2 different technologies that are being developed to extract this energy basically with just salt water and activated carbon. So one of my students came to me and said, why don't we try and combine this with microbial fuel cells? And I said, of course, that was the craziest idea I ever heard, and it will never work. Whereupon she told me that she got 65 times the energy capture and 46 times the power, more power than had ever been produced in a capacitive system like this. Shows you what the professor knows. But one of these problems with this system is it's non-continuous. You have this one cycle over here where you're harvesting energy, and then you have all these 3 other cycles where you're really not doing anything. And that's a very discontinuous process. And so she said, well, I can fix that. I said, really? Yeah. She goes, well, it's like flow batteries. Flow batteries. What's a flow battery? A flow battery is where it's a method to store energy. And what you do is you take 2 solutions and you charge them up, and then as you charge them, you put them into a holding tank. And then when you need electricity, you flow them back through the essentially the fuel cell now, if you will, and you create that energy. So you get the energy back. When you have excess energy, you recreate the species, and so it's a reversible. You're moving the chemical and oxidizing and reducing it. Now, flow electrode system is just like that, except instead of moving the chemical, you actually move the whole electrode. Okay, so how would that help us here? Well, instead of doing 4 cycles, if you take 4 reactors and now you move the carbon from reactor to reactor, you move it from the charge reactor to the open circuit reactor to the discharge reactor and then back to the next open circuit reactor, you actually can get continuous energy from these 2 systems. And so it looks something like this. These are just different concentrations of carbon, but you can see here that you're getting this constant current generation now from these reactors, and you now have a continuous source of energy at the same potential, and that's something that people can use to make energy. Okay, 2 more technologies. Anybody ever see a little baby with a diaper get in a wading pool? What happens to that diaper? Gets really big, the baby sort of falls over like, what happened here? So we know that when they get wet, the hydrogels in those diapers expand. But what you may not realize is that, sure, they expand from dry to being wet, but when they're in a salty solution, they're not quite as big as when they're in a non-salty solution. And so there's a difference in swelling between those hydrogels being exposed to salty water and non-salty water. So I had a postdoc who came up with the idea, and she said, well, why don't we just kind of create a mechanical device where we alternate flowing in salt water or fresh water into this tube of hydrogels, and you essentially create this mechanical turbine to drive power generation from these hydrogels. I think this is really cool. I'm not sure it's practical, but I think it's really cool. But actually, the energy, she estimated, she said, well, if we could scale this up, we'd extract about 3,000 joules in an hour per cubic meter. And, you know, that's not too far away from what some of the red experiments are looking at, or the pressure retarded osmosis experiments are looking at. So maybe it's not so far-fetched. Okay, so I saved the best for last. This is the newest idea on the block. And this one is related to something called a thermally regenerated battery. And we're not really quite sure whether to call it a battery or fuel cell, but it really is more like a battery. So the power densities we've gotten out of CatMix so far are on the order of about 1/10 of a watt to a few tenths of a watt per square meter of membrane area. Reverse electrodialysis, maybe 1 watt per square meter or several watts per square meter if you use brines. Pressure retarded osmosis, typical numbers, 1 to 10 watts per square meter, something in that range. What if we could get more out of those systems? Then we might be able to make this economically attractive. So I had a postdoc who came up with a process to increase the power output using a thermally regenerated solution where in the first cycle at room temperature generated 115 watts per square meter. In successive cycles produced about half that, but 60, still better than any of those. And actually, if you elevate the temperature, which is better for using a thermally regenerated solution, we've actually gotten up to a couple hundred, close to about 1/4 of a kilowatt per square meter. So how does this magic process work? Well, it's based on some very, very simple things. And the first is copper. When you put copper in water, the copper is hydrated and essentially surrounded by water molecules. And if you put a piece of solid copper in there, and then you put some ammonia into that water, what happens is you displace the water molecules with these ammonia molecules, and you now create a different potential because of the association of that copper with the ammonia rather than water. In fact, you create a potential difference of about 0.4 volts. So the idea is, let's take this system, create 2 chambers, copper electrodes on both sides, copper salt solutions on both sides. These are readily available materials. Put ammonia only in one side. And now that anode is going to corrode. When it corrodes, it creates about 0.4 volts. It creates a current. That current, actually current moves in the direction opposite of the electrons. The electrons go this way. And now at the cathode, you electroplate onto that electrode copper. So you're oxidizing away an electrode and depositing it on another one. You say, well, okay, that only gets you so far. That's right, and eventually these two electrodes stop producing current. So you take a little bit of waste heat and you distill off the ammonia out of this chamber. It hasn't gone anywhere. And you put the water back in there, the salt, the copper, in this case copper nitrate solution, and then take that ammonia and you put it effectively in the other side. So all your copper was deposited here, and now when you put that ammonia in, the same thing happens but in the other direction. You get the electrons flowing here, you now pull off that copper you just electrodeposited, and you now re-put it back onto the anode. And you can imagine at the end of that cycle, when you switch it, you're back to where you started. So this is a way to use a waste heat source for the distillation of that ammonia. All you need to do is distill the ammonia off and to generate a lot of power. The other essential thing you need from this is that you can stack these systems because you want to be able to bump up the voltage from 0.4 volts. So you can put these together, and this is just showing you two of these together produce twice as much power as one of these on the power curve. And that the cathodes are pretty good. It's the anodes that we have to improve a little bit. And so we've been working now on the chemistry. I mean, this is very proof of concept, but we can now start to work to optimize this chemistry. And so, for example, just increasing the concentrations of ammonia in the system and now also increasing copper concentrations, we can increase the power. And as I mentioned, by increasing temperature, we can do that as well. So that's really what I wanted to talk to you about today. I wanted to say, if we're going to have an energy sustainable water infrastructure, we're going to have to go out and find our own sources of energy. Why not start to look at the very thing the water industry uses every day, water, but maybe in a little bit different way. So instead of throwing away that wastewater, try and use that with some salt solutions, either seawater or solutions generated on site or with waste heat. Or look at creating technologies where just with waste heat alone, whether that's from an industrial plant or a power plant, remember any power plant that produces a gigawatt of electricity also produces about 2 gigawatts of waste heat. So if we can make any sort of dent in that, if we just get 5% of that energy, we might go from 33% to closer to 40%. That would be a big change. And so we have these green energy, we have blue energy, and let's see where this all leads. Of course, my research group and the thermal regenerative battery is the idea of Fang Zhang. They say hi. And I'd like to acknowledge my collaborators and sponsors, but especially KAUST, who helped to fund this most recent work. And that's my presentation. Oh, and a plug for ES&T letters. You can't come to the Clarke Prize conference where David Sedlak is about to receive the Clarke Prize and become the editor of ES&T without reminding you that there's ES&T letters too. So thank you very much.
All right, we can take a couple questions. Let's see if we have some. There's okay. One up here and near the front.
Yep.
I have a question about the capacity. Cap mix, the system. Based on my understanding, one of the limitations of the energy harvesting is the reversible, like the leakage of during the charge or discharge process. How tightly the ions will be absorbed onto the in the double layer.
Right.
From the materials point of view, what's the new development in this area, and What's the next trend?
So, yeah, there's a couple things with cat mix. One is charge leakage. Charge leakage isn't really too much of an issue at lower force charging densities. It becomes much more of an issue the more you try and break open that window to increase the window in that size. The other way you can increase the window is actually by treating the carbon so that it naturally has a rise or fall potential in the low concentrate solution. So you actually are able to increase the window in height while you're trying to increase it in length. So perhaps if we can increase the height, that we don't have to go and charge it so high and then run into a problem with charge leakage.